Here's our second problem. A 4-element uniform linear array is placed along the z-axis with spacing d equals lambda over 2. All elements have equal amplitude and zero progressive phase shift, which means broadside operation. We need to find the array factor, all null angles, the half-power beamwidth, and sketch the pattern. Let's follow our 5-step method. Step 1. Identify the parameters. We have n equals 4 elements. Spacing d equals lambda over 2 and beta equals 0 because all elements are fed in phase. That means broadside, maximum radiation perpendicular to the array. Now we need the phase parameter psi. It equals kd cosine theta plus beta. K is 2 pi over lambda, d is lambda over 2, and beta is 0. Multiply. 2 pi over lambda times lambda over 2 gives pi. So psi equals pi cosine theta. This single expression is the key to everything that follows. Step 2. Write the array factor. The general n-element formula from D12 is sine of n psi over 2 divided by sine of psi over 2. We substitute n equals 4 and psi equals pi cosine theta. The numerator becomes sine of 2 pi cosine theta. The denominator becomes sine of pi cosine theta over 2. To normalize, we divide by n equals 4. Quick check at theta equals 90 degrees. Psi goes to 0, and by L'Hopital's rule, the ratio approaches n, so AF normalized equals 1. Good. The maximum is at broadside. Step 3. Find the null angles. The array factor is 0 when the numerator is 0, but the denominator is not. Sine of n psi over 2 equals 0 means n psi over 2 equals m pi, where m is plus or minus 1, 2, 3, and so on. Substituting our values, we get cosine theta equals m over 2. Now we check each m. For m equals plus or minus 2, cosine theta equals plus or minus 1, which gives theta equals 0 and 180 degrees. But at those angles, the denominator is also 0, so these are main beam peaks, not nulls. For m equals plus or minus 1, cosine theta equals plus or minus 1/2, giving theta equals 60 and 120 degrees. The denominator is not 0 here. These are true nulls. For m equals plus or minus 3, cosine theta would need to be plus or minus 3/2, which is impossible since cosine is bounded by 1. So the nulls are at 60 degrees and 120 degrees. Step 4. Find the HPBW. We set the normalized array factor magnitude equal to 1 over root 2, which is 0.707. Looking at the graph, the array factor curve crosses the half-power line at approximately 76.8 degrees and 103.2 degrees. The half-power beamwidth is the difference, about 26.3 degrees. Notice how much narrower this is compared to the half-wave dipole's 78 degrees. 4 elements already give a dramatic beam narrowing. Step 5. Sketch the pattern. The polar plot shows the main beam at theta equals 90 degrees, pointing broadside. Nulls appear at 60 and 120 degrees, exactly where we calculated. Between the nulls and the end-fire directions, small side lobes appear. The pattern is symmetric about theta equals 90 degrees because the array is broadside. Notice the figure of 8 shape of the main lobe is much narrower than a single dipole. This is the power of arrays. Here's the 3D view. 4 dipoles along the z-axis create a narrow pancake-shaped beam in the broadside plane. The null cone at 60 degrees is clearly visible. With just 4 elements and half-wave spacing, we already achieve a 26-degree beamwidth and 2 distinct null angles. Let's box our answers. Part A. The normalized array factor is 1/4 times sine of 2 pi cosine theta divided by sine of pi cosine theta over 2. Part B. Nulls at 60 degrees and 120 degrees from cosine theta equals plus or minus 1/2. Part C. HPBW, approximately 26 degrees. Part D. The polar pattern shows a narrow broadside beam with 2 nulls and small side lobes. Arrays are how you shape beams. More elements, narrower beam, more nulls.